A 10-meter uniform beam of weight 101 newtons is supported by two ropes at the ends. If a 61-kilogram person sits at 2 meters from the left end of the beam, what is the tension left in the rope? Okay, so again, this is a problem that involves torque. It's actually kind of similar to the one tiger problem we had earlier, in that it involves tension and torque. Well, it involves converting forces and torques back and forth. It's actually not as hard as you'd think once you really draw a good picture. So let's do just that. Let's draw a picture. And we're finding tension in the left rope again. So yeah, let's just draw. Nope. Let's draw two separate ropes. And let's draw a beam. Okay, so that's our wonderful beam supported by two ropes. This length here would be 10 meters, right? This beam is 10 meters long. It's really 10 meters from this rope to that rope, but you know. Now let's say there is a person here. I'll just draw an oval, and he's 2 meters here. Doesn't look like much a person, but you know, that'll have to do. And we're gonna draw one more. Well, not really. We're not gonna draw something. I'm just gonna note one thing. The center of mass is directly in the center of this beam, right? It's uniform weight, so it just makes sense. Like the center, the main area we'd measure the force by would be the center, right? So I'll just draw an arrow downwards or something. And that's 5 meters, right? So let's draw a free body diagram first. Let's put a little dot by everything that has an effect. So you have the person, he has weight, the beam that has weight, and then you have two ropes, right? So these are all going to be part of our free body diagram. So let's make that free body diagram. Let's see. So you have the two ropes, right? Those do not necessarily support an equal amount of weight. I just want to note that right away. There's no law stating that if there's ropes in a problem, they have to have the same amount of, force, right? So then let's say our person obviously has weight, which is, no offense, but yeah. And let's say that weight is force of gravity, right? So FG1. And the beam also has a weight, and that's FG2, right? So what I'm saying here is the ropes point up. They have an upwards force because the beam is horizontal, the ropes are vertical. It just makes sense. We're not told otherwise. And obviously gravity is downwards, so that's exactly it. And question, is this beam moving? And this is just a question I've made myself to get to a point to try to say something. We're going to go ahead and assume that the beam is not moving. So what can we deduce from that? We can deduce that since it's not moving, there is no acceleration, right? Because things that aren't moving don't have any velocity, which means there's a constant velocity, which means the acceleration is 0. And when I say constant velocity, I mean the velocity is 0, right? So let's make a good old Newton's law sandwich. So here we have T1 and T2 going in the same direction, so T1 and T2 are both positive, minus, and I'll put the FG's in brackets, so FG1 plus FG2, right? And these and this is actually step 2. What? This is my bad. So this all is step 1. It's drawing a diagram. And I need to put the weight. Okay, wait, hold up. Please hold. kg. I mean, yeah, and 101 newtons. I'll go ahead and put that there. Let's see where we okay, here. Let's see. And this all equals 0. The thing's not moving, it's not accelerating. So, from that we can say T1 plus T2, the two tensions, equal the force of gravity, right? E2. Okay. But that's not enough, and I'll prove it in a second once we go through the calculations. There's something else though. Let's see. So you have this beam, right? And it's we can actually say that one of these uh, areas where the rope connects to the beam is a fulcrum. I don't think it matters which one you put, because mathematically you'll get the same value just from, you'll get, it'll just mathematically make sense either way. But I'm going to go ahead and just assume this this fulcrum over here, or this rope connection to beam, or whatever you want to call it. This part is the fulcrum. And that's just because I worked it out this way. So this is still, so as you can see, by the way, we have a lot of diagrams, but it's all just to make our life easier, though it would be more useful if you understood them. So let's see, you have, what torque does the rope have here? Well, the radius from the perspective of the plane of rotation, or the plane of motion, is 0. And that sounds complicated, but basically it's saying there's no perpendicular force. This would move, if there was a force this way, it would move the fulcrum, which would translate the entire plane of rotation. It wouldn't rotate the plane of rotation. Yeah, and then you'd have the person, right? So the person is applying a torque that way, right? Because of force of gravity. To make more sense of that, I guess you could say force of gravity is perpendicular to this plane of motion, right? The plane of motion is completely horizontal. The fulcrum is connected to the plane of motion. The guy is on the plane of motion, and he has a force downwards, which is perpendicular to something horizontal. So let's just say that I labeled that as torque 1, so let's call it torque 1. And now you have another torque here. This is the torque of the beam. Why is it in the center? Center of mass. Yeah, so let's just draw a dot there and a dot there. So you have, and let's call this tension 2, right? So then, what is counteracting these forces? Or what's not forces? Torques, sorry. That is the tension. This rope is pulling up on the torques, right? So yeah, let's call this torque 3. So this correlates to the tension 2. This correlates to FG1, and this correlates to FG2, right? So let's actually first state. Wait, before I make the calculations for the torques, we need to piece it all together. So this beam isn't rotating, right? It's not going up or down. even though there are different torques being applied. What does that mean? That means there's rotational equilibrium. This is kind of similar to the last problem, but except a lot more complicated. Or, well, not a lot more, but this is quite a bit more. Okay, so then you have T1 plus T2. Actually, I made these negative, but it doesn't matter. It doesn't matter. Minus T3, or not T technically. That's not there. Equals 0. So what does this mean? This means T1 plus T2 equals T3. All we've done is add T3 to both sides. Or not, again, not T, but you get the idea. So, and this is all 2, it's formulas, step 2 of the 5-step process. So, now we move on to the actual calculations, the fun part. Not quite, but you know, let's pretend it's fun. So first let's work out FG1 and FG2. Well, we already have FG2, so let's see. Let's go ahead and start with FG1. So FG1 equals, so this is FG1, so it's 61, it's FG equals mass times gravity, right? So this is 61 times 9.8. What do we get? Okay, let me check. We get, actually let me just go ahead and, now you see 597.8, ignore that. 597.8. Okay. Now, oh, by the way, did you know you could do that? You could Google calculations. It's kind of cool. Okay. So, how about FG2? Oh, this is a tough one. Well, FG2 equals that. Whoa. Oh, by the way, this is in newtons. Newtons, okay. And I'm just gonna check my work to make sure that's what I put. That is, okay. That means T1 plus T2 equals 597.8 plus 101. Now to find the actual tensions. And we do that by finding the torques. You can tell this is some real thrilling work. So, let's see. Torque 1. What is torque 1? Torque 1 is that which means, okay, what's the radius here? The radius is 2, right? And the force is, this is 61 times, it's 597.8. So let's write that out. 597.8 times 2. I'll just find that calculation in a second, but first let's then go to torque 2. So torque 2 would be the board. Okay, so since this is the center of mass is 5 meters in, and the force of gravity is 101, it's 101, the force is 101, and the radius is 5, which means that equals 505. That's an easy calculation. And this is in Newton meters. So that would be 1195.6. Okay. Actually, it looks like we're flat at time. Join us next episode. where we find the answer